Now, what about a quantitative view? This gives us a good qualitative view of what the field looks like. What about a quantitative view? What's a quantitative description? Well, we've used the idea that the electric field, and I will use the symbol capital E, and it is a vector, so this is a vector field. We've used the idea that the electric field kind of depends on the strength of the force and the direction of the force also that acts on a test charge. So we'll say that this electric field is somehow related to the force acting on a test charge. But we want the electric field to only depend on the charge here, not on the test charge. So we've used this test charge to determine the qualities of the electric field, but we don't actually want the electric field to depend on the specific test charge we use. We want the electric field to be created by this charge here and really have nothing to do with what particular test charge we use. So we know the force that acts on the test charge depends on the magnitude of the charge of the test charge. So to remove that dependence, we will divide by the magnitude of the test charge, and we'll define our electric field in that way. So we'll use a test charge to determine the properties of the electric field, but we'll remove any specific dependence on the particular test charge that we use by dividing off the magnitude of the test charge. So what do we end up with? The definition of the electric field that we'll use for some charge here will be the force vector acting on a test charge divided by the magnitude of that test charge. Well, what does that mean? We know that well, in terms of the magnitude, we know that E is then going to be Q, E is equal to K times Q, the charge here, times the magnitude of the test charge, divided by R squared. And if we divide off that test charge, we end up with the electric field is equal to KQ over R squared. And there's the magnitude of the electric field created by our charge Q here. We can actually turn this into a vector definition by just saying this electric vector is then equal, is equal to this magnitude KQ over R squared times a unit vector R hat, where R hat is a different kind of unit vector than X hat, Y hat, Z hat. R hat is a unit vector which will always point away from the origin, no matter where you are. R hat always points away from the origin, and it always has a magnitude 1. That's why it's called a unit vector. So what does this tell us? If Q is positive, E points in the direction of R hat. So if Q is positive, E points away from Q. If Q is negative, E will be in the negative R hat direction. In other words, toward the charge. So that works. If we have a positive charge, the electric field points away. If we have a negative charge, the electric field points toward the charge. So, very, very good. This gives us a very nice quantitative definition for the electric field created by a particular charge, whether it's a positive or a negative charge. This gives us a good definition for that electric field that we can use, and we'll do some calculations using that in just a second. Before we go on, let's take a look at what the units are for the electric field. What are the units of E? Well, let's come back up here. The units of the electric field will be the units of force divided by the units of charge. Well, the units of force are what? Newtons. The units of charge are coulombs. So the units of the electric field will be newtons per coulomb. Luckily, we do not have a particular new unit to go along with this, so we'll just say the units of the electric field are newtons per coulomb. There'll be another combination that we can use later on, but for now we'll say newtons per coulomb. But we don't have a single unit to define for that. So, very good. Units for electric field, newtons per coulomb. What we're going to do next is stick some numbers in here and actually calculate some electric fields. Okay, so let's stick some numbers in here. And calculate some electric fields. Let's imagine we've got a coordinate system here. Let's put a charge of, let's say, 1 microcoulomb at the point 2 meters, 1 meter. And let's figure out what the electric field is at the point 5 meters, 1 meter. So 1, 2, 3, 4, 5. So let's figure out what's the electric field at this point 5 meters, 1 meter. Let's figure out the electric field at that point due to this charge. So we'll call that electric field, we'll call it E1. So let's figure out what is E1. I would suggest that you calculate the magnitude of the electric field using the magnitude of the charge, and then, knowing what we know of the direction of the electric field, put the direction in afterwards. So let's figure out what the magnitude is. We know the magnitude of the electric field will be K times the magnitude of our charge over the distance squared. So let's figure out what that is. Well, K, we know, is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, times the magnitude of the charge. Now, what's the magnitude of the charge? 1 microcoulomb. In order for the units to cancel, we have to put that in terms of coulombs. 1 microcoulomb is 1 times 10 to the minus 6 coulombs. So there's the charge, divided by R squared. Now, what's R? R is the distance between the charge and the point at which we're calculating the electric field. So R is this distance here. So what's that? We're going from the point, oops, sorry, I wrote down the wrong thing here. This should be 1 meters, no, that's right, I had it right, 2 meters, 1 meter, sorry. So we're going from the point 2 meters, 1 meter to the point 5 meters, 1 meter. What's that distance? Well, that's going to be 3 meters. So R is 3 meters. So R, 3 meters, and we want R squared. There we go. So we just take 8.99 times 10 to the 9th times 1 times 10 to the minus 6 divided by 3 squared, and what do we get? We get a magnitude of E1, which is 999. And let's look at the units. We've got a coulomb up here. That cancels with one of these down here. We've got meters squared cancels with meters squared, and what are we left with? Newtons per coulomb. Well, that's exactly what we thought the units of electric field should be, newtons per coulomb. There we go. We've got the magnitude of the electric field. Now, what's the direction? We've got to make this a vector. We know the direction of the electric field points away from positive charges. So, away from this charge at this point will be directly away from the charge, will be exactly in that direction. Well, what's that direction? That's in the x-hat direction. So we can say E1 is 999 newtons per coulomb in the x-hat direction. And there we go. There is E1 in a full quantitative form, magnitude and direction. Okay, let's try another one. Let's figure out what the electric field is, let's say at the point 5 meters, 2 meters. So, let's get rid of this. We'll keep the same charge here. Let's figure out what is the electric field at the point up here. 5 meters, 2 meters. Let's figure out that. We'll call that E2. So what is E2? Well, quantitatively we know, we can at least draw this in, that the electric field, again, is going to point away from the charge, directly away from the charge, so we know it's going to look something like that. Well, maybe something a little bit more like that. Okay, directly away from the charge. So what do we get? Again, we know that E2 is going to be kq over r squared. So do we get the same number? Well, no, because r is going to be different. R, again, the distance from the charge to the point at which we're calculating the electric field, that is going to be different than the 3 meters that we had last time. So how do we figure out r? Well, we're going to have to use Pythagoras here. We've got a triangle here where this side is 3 meters and this side is 1 meter. So what's r? Well, r we know is going to be 3 meters squared plus 1 meter squared square root, or 3 squared 9 plus 1 squared 1, that's 10, root 10, so r is equal to 3.16 meters. R is 3.16 meters. Or r squared will be 10. Since we want r squared, we'll just stick in 10 meters squared down there. We could do that. So what do we get? We get E2 is then 8.99 times 10 to the 9th times 1 times 10 to the minus 6 divided by 3.16 meters quantity squared, which we know is going to be 10 meters squared. Multiply that all out, divide, and what do we get? We get that E2 is equal to 899, and again, units, meter squared cancels, newtons per meter. There we go. So there's our magnitude, 899 newtons per meter. Let's see if we can't break this down into components. We've got E2 is no longer horizontal, so it's no longer in the x-hat direction. It's going up at some angle. We can break this down into E2x and E2y. But what's this angle here? We call that theta. What's that angle? Well, we know that that line is a straight line right here, so that angle theta must be the same as that angle theta. So we can figure out what theta is. We know that tan theta is equal to opposite over adjacent, or 1 meter over 3 meters, or 1/3, 0.333, or theta is equal to the inverse tan of 0.333, which gives us 18.4 degrees. And so what do we have? We've got E2x is going to be, E2x will be E2, let's rewrite E2 up on the top here, on the hypotenuse, E2x will be E2 cos theta, or 899 newtons per meter cosine 18.4 degrees. We multiply that out and we get 853 newtons per coulomb, while E2y will be 899 newtons per meter sine 18.4 degrees. Multiply that out and we get 284 newtons per coulomb. There we go. And so we can write our final result for our electric field E2. Erase this here. And what do we get? We get E2 vector is equal to the x component, 853 newtons per coulomb x hat, plus 284, newtons per coulomb y hat. There we go. So there is our final result. Another way of writing this is we can say that E2 is equal to 899 newtons per coulomb at an angle of 18.4 degrees above the x-axis. So that would be another way of writing E2. We can write it in component form, where we give the x and y components, or we can give the magnitude and direction form, where that's the magnitude, and then at an angle of 18.4 degrees above the x-axis. that is the magnitude and direction. So we can describe E2 in either of those two ways. Okay, great. Let's try another one. Let's find the electric field at the origin. So, given the same charge, 1 microcoulomb at this point, what is the electric field at the origin? We'll call that E3. So, what is E3? So, let's get rid of all of this part. All right, so what's the electric field right here? Again, remember, the electric field always points away from positive charges. Away from the positive charge here is going to be in a direction that looks like that. So E3 is going to look something like that, coming from a straight line from that point there. Again, let's figure out what's the magnitude. Whoops, we don't need this up here. E3 is going to be KQ over R squared. Again, we're going to have a different value for R. R, the distance from the charge to the point at which we're calculating the electric field, is going to be this distance here. Again, we'll use Pythagoras. We've got a triangle, a right triangle with a side of 2 meters and 1 meter. So R is going to be 2 meters squared plus 1 meter squared, square root. 2 squared is 4, plus 1 is 5, root 5. So this is going to be root 5, which is 2.24. So R is 2.24 meters, or R squared is 5 meters. Whoops, sorry. R, 2.24 meters. R squared, 5 meters squared. So what do we get for E3? Magnitude E3 is K, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times Q, again, 1 microcoulomb. 1 times 10 to the minus 6 coulombs divided by R squared, 2.24 meters squared. Multiply that out, and what do we get? We get E3 is equal to 1.80 times 10 to the third newtons per coulomb. Now, let's just think just for a second. The first value that we found at this point, something like here, was 999. The next point up here was 899, less than the first one. Why was this one less than the first one? Well, it was a little bit further away. Further away means a weaker field, so that one was a little bit less. Now, this one, 1.80 times 10 to the third, or 1,800. Why is that larger than the first two? Well, this point is a little bit closer to our charge than these, and so the electric field is going to be larger. Okay, that all makes sense. That seems to be consistent with what we have expected. Now, what's the direction? Well, we've got the magnitude. The direction of this is at some angle theta here below the negative x-axis. Well, since this is a straight line, we know that angle has to be the same as that angle, so we can figure out what that is. We know tan theta is equal to opposite over adjacent, 1 meter over 2 meters, or 0.5. Theta is going to be the inverse tan of 0.5, which is 26.6 degrees. So one way of describing E3 is that E3 vector is equal to 1.80 times 10 to the third newtons per coulomb at an angle of 26.6 degrees below the negative x-axis. So this is below the negative x direction, so below the negative x-axis. There we go. There we've got one description for our vector E3. We can break this down into components. If this is our magnitude E3, we can break this down into E3x and E3y. Let's get rid of this up here. What do we have? We've got E3x is equal to the magnitude 1.80 times 10 to the third newtons per coulomb cosine 26.6 degrees. But wait a second, this is pointing in the negative x direction, so we need a negative sign there. This gives us a value of negative 1.61 times 10 to the third newtons per coulomb, and there's our x component. What's our y component? E3y. This is going to be E3 sine theta, or 1.80 times 10 to the third newtons per coulomb sine 26.6 degrees. Likewise, notice this is pointing in the downward direction, so we're going to have a negative y component, so we've got to put another negative sign there, which leaves us with E3. E3y is negative 8.06 times 10 to the 2 newtons per coulomb. And there we go. We can then write that E3 is equal to negative 1.61 times 10 to the third newtons per coulomb x hat minus 8.06 times 10 to the 2 newtons per coulomb y hat. And there we have the component form of E3. So we've got E3 in the magnitude direction form and E3 in the xy component form. Okay, good.